So very first thing, what is a database? A database is basically just any kind of system that's designed for storing lots of data, and typically it's a system made available on the network which handles many incoming requests, and those requests can overlap. Most often the database has been given a defined schema, basically an imposed structure on the shape of the data, and usually the database has some mechanisms that ensure the structure gets preserved, that no one can insert, modify, or remove any data in a way that will violate the schema. To these ends, handling many overlapping requests and preserving a schema, preserving a data structure, most databases handle requests in what are called transactions, which is basically a defined independent unit of work that is enacted upon the data. So one client contacts the database and conducts one transaction, while simultaneously perhaps another client is contacting the database and performing another transaction. And the idea is that the database is somehow making sure those two separate transactions don't interfere with each other. Ideally, transactions conform to what's prescribed by the acronym ACID, which stands for atomicity, consistency, isolation, and durability. What atomicity means, what it means for a transaction to be atomic, is that the entire transaction is performed all or nothing. So either all the modifications made in a transaction are committed to the database, otherwise all the modifications are rejected. And if rejected the transaction, then all of its modifications, it's like they never happened. So in the course of a transaction, something might arise that will require the transaction to abort effectively. And so all the changes made up to that point in the transaction, they have to get rolled back. They have to be undone. And then, of course, the client making this transaction should be notified that, hey, we aborted your transaction, so try again later or something. Now, you're probably wondering, why would a transaction get aborted? Well, there are several reasons this might happen. One reason is because something is happening in another transaction which then interferes with your transaction, and one of them has to be aborted. That's a possibility. It could be because there's a power failure or some sort of crash or some kind of internal error in the database itself. The important thing in all these circumstances is that whatever modifications are being performed in a transaction, they should be all or nothing. So we either take it all or we drop it all. What consistency in ACID means is that when a transaction completes, it should leave the database in a so-called consistent state, meaning a state consistent with all of the rules, all of the constraints imposed in the schema. So if the schema says that the data should conform to such and such structure and the values should conform to such and such rules, every transaction should leave the database conforming to those rules. Isolation in ACID refers to the property that transactions should be totally independent of each other. They shouldn't interfere with each other in any way. Or actually, to put it more accurately, overlapping transactions should not interfere with each other. Obviously, if one transaction updates the value of one piece of data, you want that new value to then be subsequently read by any subsequent transactions which read that same piece of data. The issue with concurrency is when you have multiple actors all trying to act on the same data at the same time. You have different hands all reaching into the same bag, not knowing what the other hands are doing. And without proper isolation of transactions, this could lead to situations where, say, you have two overlapping transactions, and while one transaction is updating two pieces of data, the other transaction is trying to read those two pieces of data, but because of happenstance of timing, the transaction reading the data gets one of the values updated but not the other one. And depending what your application does, this could be very undesirable. You might have written your code such that you assume that when you update multiple values, that anyone reading the database is going to see all of those updates as a whole, rather than getting a mix of new updated values and old out-of-date values. So again, the ideal is complete isolation of transactions, such that when a client connects to the database and makes a transaction, in the course of that transaction, it's as if that single client has the database all to itself and no one else is making modifications or reading data. Now, the trade-off there is that if you have completely isolated transactions, the only way to achieve that really is to serialize all the transactions, such that while one client is making a transaction, all other clients have to basically just wait. And so obviously from the perspective of the clients that are forced to wait, the performance of the database has degraded because they're sitting around and waiting for it. So in practice, databases typically offer different levels of isolation. It's a configurable option of how much isolation do you really need. Do you need total isolation, or are you willing to relax the rules a bit to allow for more overlapping transactions to get on with their work? These different isolation levels are something we'll talk about much later. Finally, the durability of a transaction simply refers to the property whereby once a transaction completes, or commits as we say, then all of the changes it's made to the database, they get preserved. The data should persist, and it should persist even in the event of, say, power loss or crashes. Now, of course, systems do go down, but the point of durability is that in such eventuality, the database should be able to be restored to its last good state. So, it's these four properties of transactions, atomicity, consistency, isolation, and durability, that should help convey why it is desirable to use databases, why, rather than have your application store data in just some makeshift format, which your application then writes to files, as soon as you recognize that your application makes use of a lot of data, it makes sense to then pass that job off to a database so that you don't have to, in your own code, provide for atomicity, consistency, isolation, and durability, because providing all those things is really damn tricky. The standard file system itself does not offer those features. In this unit, we're going to specifically learn about relational databases. Relational here refers to what's called the relational model of data, which was devised by a guy named Edgar F. Codd in about 1969. The relational model for structuring data is one of a few alternatives. There's the so-called hierarchical model, a network model, an object model. The relational model, however, is by far the most dominant. The large majority of databases in use out there are relational databases. And in fact, the term RDBMS stands for Relational Database Management System. And this term, RDBMS, refers to the software itself. And the reason it's called a management system rather than just a database system is because you can have multiple separate databases all under control of one program, of one database system. In common parlance, though, we just usually refer to the software not as an RDBMS or a management system, we just say the database, usually. Now, SQL, more commonly pronounced SQL, and standing for Structured Query Language, that refers to a standard language used by most databases. It's the language which clients use when they talk to the database server. The term query refers to a request for data, so when you send a request to get data back from the database, that's a query. SQL, however, is not restricted to just queries. It's also for requests to insert data or to modify data in the database. So calling SQL just a query language is a bit of a misnomer. Now, SQL, as I said, is a standard. It was first introduced in about 1974, and it's used by basically every relational database out there. However, the issue is that not all databases use exactly the same SQL language. They all have their own variations. So in practice, the SQL code you write for one database generally has to be rewritten to work with another database. Now, there are dozens of different relational database management systems out there. These five here, though, I would say are the most popular. First, Oracle Corporation is one of the big software companies around, and it built itself virtually entirely on its database product. For many, many years, all through the 90s at least, Oracle was regarded as basically the serious database of choice for the enterprise, and Oracle charged for licenses of its database accordingly. Currently, Oracle licenses go for something like tens of thousands of dollars per CPU license, meaning if you have a database server with, say, 8 CPUs, you have to pay for 8 separate licenses to run it on that server. So Oracle is very, very, very expensive. On top of being by far the most expensive option, it's also by a considerable margin the most complex. Microsoft's database, which they call SQL Server, I would say is also one of the more complicated options, and also one of the more expensive, though I would say not nearly so much as Oracle. It is considerably less complex, and the licensing cost is considerably less shocking. Now, despite having SQL in the name of its product, Microsoft's database is not that much more conformant to SQL than any other database out there. Nor would I say it's more divergent, but Microsoft actually has codified its own extensions of the standard SQL language, what it calls T-SQL, T as in transact. The MySQL database is so called because the original programmer named it after his own daughter named Mai. This programmer and his partner founded a company around this database product, and they actually released MySQL under an open source license, and MySQL today is still the most popular open source database. Now, of course, the company needed money, so they sold an enterprise version of the same database with a few extra features. Back in 2008, this company was acquired by Sun Microsystems, but Sun Microsystems went under a few years later and got acquired by Oracle, so now Oracle actually owns the rights to MySQL. This has caused a lot of consternation in the open source community because Oracle is not exactly the most friendly company towards open source. Oracle, though, of course, can't outright revoke the existing open source code base, so it remains to be seen whether Oracle successfully undermines MySQL as an open source product or not. And again, despite having SQL in the name of the product itself, that doesn't guarantee at all that MySQL conforms any better to the SQL standard than any other database, and in fact MySQL is kind of one of the more divergent SQL databases out there. The happy news is that, well, if MySQL is on the wane as the open source database of choice, well, Postgres is picking up the slack. Postgres, as it's usually called, we also sometimes say PostgreSQL. Postgres sort of gets its name as a pun on the previous database which it was sort of based on, and that database was called Ingres, hence Postgres. Postgres is my database of choice, and it's the one I would recommend starting out with. The only reservation I have of recommending it over MySQL is that Postgres is actually what's called an object relational database. So it's not just a relational database, it's a object relational. It's mixing the object model of data and the relational model together. Or more accurately, it's actually just taking the relational model and putting object features on top, which fortunately means that you can actually work with Postgres and just ignore this whole object aspect to it. You can treat it as just a plain relational database if you want. But when you go look at the documentation for Postgres, you should be aware that there's some stuff in there that is not strictly relational, it's object relational, and that explains why there's some added complexities there. Oracle actually is also the other one here, which is also an object relational database. In fact, it was the first major example of such a system. But again, I wouldn't fret about it. You can ignore the whole object aspect of these systems, and in fact that's what we will do. We'll just treat them as plain relational databases. Finally, SQLite is an interesting example. It's also open source, but what makes it unique is that whereas in all these other examples, and in fact in most database systems, they run as network programs. They run as servers listening for requests from clients, whether those clients are on the same machine or on some other machine. So when you make use of these databases, you write your own program which then contacts the database over the network. SQLite, however, is a SQL database implemented as a library. The version for Python, for example, is just a Python module which we import, and then it has classes, and those classes have methods and properties which we then use, and this library just takes our data for us and reads and writes our data to our file, and that file is the actual storage of our database. So with SQLite, there's no servers, there's no clients, it's just your application program reading and writing to this file as a database. We're just doing so with more or less the same semantics we use when we talk to a relational database, a SQL database. So, to give you one example where SQLite is used, the Firefox web browser actually uses SQLite to store all of your browser history and your bookmarks. Using SQLite for this purpose makes a lot of sense because you wouldn't want to use a full-fledged SQL database. That would require installing and having the user run a full-fledged server on their system, which is just way overkill and a huge configuration nightmare that most users are not going to manage. So for that use case, SQLite makes tons of sense. Be clear, however, that SQLite very consciously and very deliberately is not appropriate for the sort of applications usually used for a full-fledged SQL database, like Oracle or SQL Server or Postgres. So, for example, the vast majority of web applications out there, you have the web server, and the web server stores and retrieves data from a database. And in that case, you want to have a proper full-fledged database like Postgres or Microsoft SQL Server. Unless your website gets very little traffic, you wouldn't want your website to use SQLite because it just does not perform well for those kinds of scenarios. To start things off, we'll look at the relational model itself. What's called a relation is composed of both tuples and attributes. In common parlance, though, we call relations tables, and tables are made up of columns and rows. What the relational model calls attributes are the columns, and what it calls tuples are the rows. So here is an example relation, an example table. It's a table with data about planets, so we'll call it our planets table. And it has 4 columns, 4 attributes about planets. First there's the name, there's the distance from the sun in miles of that planet, there's the length of a year in Earth days for that planet, and then there's the length of that planet's day, how long it takes to rotate, expressed in terms of Earth days. Each tuple in this relation, each row in this table, represents one planet, as represented by these 4 attributes, the name, the distance from the sun, the length of the year, and the length of a day. Be clear that here at the top of the table, in dark blue, those are just the headers for the columns. That's not actually a row. Now, a key thing to understand about the relational model is that the order among the tuples, among the rows, is not a part of the data. As far as the relational model is concerned, the rows aren't in any order at all. They just happen here to be written in this particular order. Because, of course, if you present a table, you have to show them in some order. But as far as the relational model is concerned, the fact that Venus here is listed first and Mars is listed last, that's just happenstance. If we mixed the rows up and put them in a different order, it would still be the same table with the same data. Likewise, the attributes of a table, the columns, those don't have an order either. So the fact that we have the name column first is just happenstance. We could put it second, we could put it third, we could put it fourth. It doesn't matter. We could present these columns in any order and it would still be the same table. Another way of thinking about this is that this is a planets table. So each tuple here, each row here, represents a single planet. And what makes up our definition of a planet is these four pieces of data: a name, a distance from the sun, the length of a year, and the length of a day. Our table, though, contains some number of planets, and amongst those planets there's no concept of order. Each row is just one more planet. And likewise, the attributes that make up each planet, well, those don't go in any order either. These are just four independent facts about each planet. Now, in the relational model, when we wish to retrieve data from our database, we want to retrieve some data from one of our tables. That's what we call a query. And when we query a table, we don't necessarily want the whole table. We maybe only want certain rows and certain columns. When it comes to picking columns, we just specify the ones we want by name. When it comes to rows, however, we use a predicate, some test condition, to filter for the rows that we want. So when we query our planets table, we might filter for, say, the rows in which the distance from the sun is greater than 100 million miles. So that leaves us with Uranus, Neptune, Jupiter, Saturn, and Mars. And say that in our query we don't want all the columns, we just want the length of the year and the length of the day. Well, we just specify those by name. And this is the end result. This is the result of our query, which notice looks very much like a table, because it is. It has columns specifying attributes, and then it has some number of rows. So this is actually a very important concept. Any query always returns just one table. The question then is, well, what if I want a query that brings in data from multiple tables? And, well, yes, that's actually possible, but doing so will involve what's called a join, where you take more than one table and combine them into one. And in your query, once you've joined tables together, you can then, again, select for columns and also filter for rows by a predicate. So first, though, how do you actually join tables together? Say we have these two tables, a cat's table and a dog's table. The cat's table has three attributes, three columns, name, lives, and hair length. And you can see it has three rows, so it's effectively a column with three cats. And then the dog's row simply has two attributes, sex and name, and it has two rows, so effectively two dogs. Now, if we prefer what's called a cross-join of the tables cats and dogs, this is the table that results. This is what we do when we match up every row in the cat's table with every row in the dog's table. It's taking the columns of both rows and matching them in all combinations. That's why we end up with 6 rows, because the cat's table had 3 rows and the dog's table had 2. 3 times 2 is 6. When you pair up everything in a set of x things with a set of y things, the number of pairs that result is x times y. So if, say, the cat's table had 5 rows and the dog's table had 7 rows, then the result from the cross join would have 35 rows, 5 times 7. Also note that this table has all of the attributes, all of the columns of the original 2 tables. And also note that I've labeled each column with the table from which it originates, which is important here because we have both a cat's name column and a dog's name column, and those are 2 distinct columns. So just to state this all again, when you cross-join tables A and tables B, you're taking each row from table A and matching it up with every row from table B. So the number of rows you end up is the product of the number of rows in A and the number of rows in B. It's just the multiplication of the 2. But the number of columns is simply the sum of the number of columns in table A and the number of columns in table B. So this is what's called the cross join. There are also, though, what are called inner joins and outer joins. An inner join, very simply, is the same deal. We perform a cross join, but then we filter out rows by a predicate. So here we've performed the same cross join from the same 2 original tables, but then we've filtered to keep only the rows where the dog's sex column value is female. Now, at this point, you're probably a bit skeptical about the utility of joining tables together, because in this example we've taken really what are 2 totally unrelated tables, and the joining of 2 unrelated tables generally doesn't really produce useful results. If we go back though and tweak our example tables just a little bit, here changing a few of the names of the cats, and once again we do the cross join, well, now with an inner join we can filter by a predicate that is possibly useful. Here we're filtering for all the rows in which the cat's name value equals the dog's name value. So we're ending up with a table that lists names which happen to be shared by both a cat and a dog. Still not the most compelling example in the world, but hopefully you can begin to see how joining tables together might be useful. Now, the last kind of join is what's called an outer join, in which we take the inner join and then after we've filtered out rows, then we add back in any row from one of the two original tables that is not present in this result, in the filtered result. And these rows we add back in, we match them up with null values. So here, for instance, is the same inner join we just did, but made into an outer join. And whereas the inner join left us with just 2 rows, this outer join adds back in a 3rd row with the cat Fluffy matched up against null values in the 2 dogs columns. Why does the outer join do this? Well, recall in our original tables we had 3 cats, Fluffy, Spot, and Princess, and in our dogs table we had 2 dogs, Princess and Spot. And both of those 2 dogs, Princess and Spot, were included in the result of the inner join, so the outer join doesn't need to add them back in. They are already represented in the table. The cat Fluffy, however, the inner join was missing that, so the outer join adds it back in. The inner join left us without that row from one of the original tables, so we add it back in, but then we match it up against null values in the columns from the other table, in this case the dogs table columns. Now, there are actually 3 different kinds of outer joins. There's what's called a full outer join, which ensures inclusion of all rows from both tables, both of the input tables. There's what's called a left outer join, which ensures inclusion of all the rows from just the left table, which is to say if we write A outer join B, the so-called left table is A because it's the one written on the left. And conversely, a right outer join ensures the inclusion of all rows from just the right table. So if we A right outer join B, that's ensuring inclusion of all rows in just table B, not A. In common parlance, we usually don't say left outer join or right outer join. We just say left join and right join because the outer part is implicit. There's no such thing as a left inner join or a right inner join or a left or right join of any other kind. They're always outer joins. For a full outer join, you can't drop the full part. You have to always say full outer join. When it comes to inner joins, and I should say also cross joins, when it comes to inner joins and cross joins, they are both always commutative and they are associative. And commutative, recall, refers to an operation where it doesn't matter the order of the operands. So if you write A inner join B, it's the same as B inner join A, just as A plus B is the same thing as B plus A. An associative operation, recall, is one in which when you chain a succession of these operations together, it doesn't matter in which order you do them. So if you wish to inner join together A, B, and C, or cross join them, it doesn't matter if you join A and B first or B and C first. Or for that matter, we could join together A and C first and then join the result of that to B. Because inner joins and cross joins are associative, it doesn't matter. Outer joins, though, are a different matter. While full outer joins are commutative, left and right outer joins are not. So A left outer join B is not the same thing as doing B left outer join A. And when it comes to stringing multiple joins together, outer joins of any kind, full, left, or right, are not associative. So when you write A outer join B, and then outer join the result of that to C, that is different than first joining B and C together and then joining the result of that to A. So in short, with outer joins, the order of joins matters in a way that it doesn't with inner joins. A final thing to note about joins here is that it's actually possible to join a table with itself. So here, for example, we take our 2x2 dogs table and join it with itself in a cross join. And what we get back is a table with 4 columns and 4 rows, because 2 plus 2 gets us 4 columns and 2 times 2 gets us 4 rows. So that's all the gist of what you need to know about joining. There are a few more interesting things though we can do in our queries, such as say filtering for distinct rows. In other words, getting rid of duplicates. In this table, for example, we have 2 rows where the values in each column are all the same. It's 2 cats named Princess with 6 lives and long hair. If our query filters for distinct rows, then these 2 rows consolidate into 1. In other cases, it may be useful to consolidate columns that only match in certain columns that aren't total duplicates. So here, for example, if we group on the name column, we're consolidating duplicate names, leaving us with just a name column. Since we're grouping on name, it doesn't make sense to include the other columns because the values in those other columns might be different. The hair length, for example, we have 3 princesses that are getting consolidated into just one princess, but 2 rows with the name princess have long hair while the other one has short. So the question is, well, if we had a hair length column here, what would it be? Would it be long or short? And the answer is, well, neither would actually make sense. We have conflicting values. It is possible, though, to group on multiple columns. So if we group on both the name column and the hair length column, then we get back a table with the name and hair length columns in which the name and hair length together form a unique pair. So we have 2 rows with the name princess, but one has hair length short and the other has hair length long. Likewise, if we were to group on lives and hair length, we'd end up with a table with the lives column and the hair length column with 2 rows with a lives value of 6, but one with hair length long and the other with hair length short. When we group columns, it's then possible to use what are called aggregate functions. An aggregate function produces an output value by taking in all the values that get grouped together. We can then produce these output values to produce totally new columns, columns which aren't in the original table. So here we have a table of car inventory specifying a car make, car color, and then the quantity of cars with that make and color. So for example, the top row here says that we have 15 blue Toyotas. If we were to then take this table and group on the make column, that leaves us with a table of 3 rows, Toyota, Ford, and Honda. What's new here is that we're using the aggregate function sum to produce a second column. And the sum function is taking the value from the quantity column. And what the sum function does, as you might imagine, is sum together all the values from that group. So the Toyota group here has the quantities 15 and 10. So you add those together and you get 25. The Ford group here has the values 3 and 20, which you add together and get 23. And then the Honda group here just has the 1 row, so it's just the value 9 added to nothing, so we just get 9. So you can see how this is useful. Given our table of inventories of car make and color, we've gotten a table that tells us how many cars we have in total per make. For another example, we're taking the same inventory table, but we're grouping on the color column, and we're using the max function instead of sum. So we're taking the max of the quantity. And what the max function does is it takes all the values from the group and it returns the largest one. So in the blue group, we have the quantity values 15 and 9. 15 is the larger, so that's what gets returned. In the red group, we have the quantity values 10 and 3. 10 is obviously the larger, so that's what gets returned. And then in the green group, there's just one value, 20, so the max function just returns 20. I should state at this point, if it hasn't been obvious, but these 2 functions, these 2 aggregate functions, sum and max, only work on numeric values. It wouldn't make any sense on, say, a string value like Toyota or Ford. Now, last thing to say about aggregate functions is you actually can use them when you don't do any grouping. It's just that it treats the whole table as a single group. So here if we query our inventory table and tack on a sum quantity column, notice the value for that column in every row is 57, which is the sum of all of the quantities together. Now, aside from that one exception, the aggregate functions always work on groupings of rows. There are non-aggregate functions, however, what we might just call value functions, and also we can use a number of operators to produce new values. So here, for example, we have a table with widths and heights, and in querying this table, we're tacking on 2 columns, one which is the multiplication of width and height together, and another column which uses the square root function to get the square root of the height. So in the bottom row here, for example, the width times height column has the value 16 because the width is 2 and the height is 8. Multiply those together, you get 16, and the square root height column value is 2.828427 because that's the square root of 8. So again, what's going on here is we're using operators and functions provided by the database to produce new values, to produce new columns using values from other columns in the same row. Now, the question is, why do I need my database to do this stuff for me? Can't I just get the data from the database and then do the operations myself in my own code? And the answer is yes, you can. The issue, though, is whether or not it's done more efficiently for your purposes in the database or whether it's easier to do it in your own code, which is more efficient. Depending upon exactly what you're doing, that answer might change. Generally, I would say it's better to let the database do as much work as possible because the database is generally optimized for doing these sorts of things on large sets of data. Does this always hold true in all cases, though? No, it probably doesn't. So that you'll probably find there are cases where you're better off doing the work outside the database. Now, I did stress that in the relational model, the order of the rows of our tables is not a facet of the data. If you take any table and you mix up the order of the rows, it's still the same table. Of course, though, when our applications query data from the database and we get it back as this result set, a bunch of rows, quite often we want those rows in some kind of order, because, say, we're going to present them in a certain order, like, say, alphabetical or something. So relational databases actually do allow us to request our queries to come back in some certain order. Even if the data itself, as stored in the database, has no order, when we get it back, when we query it, then we want it in some order. We want it to be presented to us in some order. So, for example, here again we have our table of cats, and if we want to query this table but get it back in some certain order, we specify which column we want to sort on. In this case, we specify the lives column, and we specify whether we want this order to be ascending or descending. Ascending, very confusingly and asked backwards, means that the values get larger as we go down the table. So as we descend the table, the values get larger. It makes no sense. It's totally backwards. But we say that the values are ascending in this order because from the perspective of the program making the query and getting back the results, in our code we get back this list of rows. And in the list we want the first thing to be the smallest value, and we want the values to ascend to get bigger as we read through the list. So that's why it's called the ascending sort, because the values as we go downwards they get bigger, and so as we go from left to right, from first to last in our list, they get bigger. That's why it's called ascending. A descending sort, as you can imagine, is the precise opposite. The values get smaller as we go down the rows, as we go from the first row to the last. And the last thing to say about sorting is you don't have to sort on just numeric values, you can also sort on text values. And as far as text is concerned, values lower in the alphabet, later in the alphabet, are considered greater values. So if you do an ascending sort on a text column, that's effectively sorting alphabetically. A descending sort would be reverse alphabetical. So by this point we've actually now covered all the core concepts of querying data, but what about actually adding data into the database, or updating data, manipulating data? Well, when it comes to adding a row for a table, this is called an insert operation. And unsurprisingly, if you want to insert a new row, you have to provide a value for each column. So here in our cats table, we're inserting a new row, and we're providing a name value mittens, a lives value 2, and a hair length short. And now we have a cat, mittens with 2 lives, and short hair. When it comes time to remove rows from a table, to delete them, what we do is we specify a predicate used to filter rows, to select rows, and then delete them. So here in our planets table, if we delete rows by specifying a predicate of distance from sun greater than 100 billion miles, that's effectively specifying Uranus, Neptune, Jupiter, Saturn, and Mars, and then deleting them. If we want to change data in existing rows, this is called an update operation, and first we specify which rows we want to update with a predicate, and of course we specify which column or columns we wish to update with a new value and what those new values should be. So here we're updating simply the column lives with a value 5 in all rows where the name value is princess. So whatever number of lives these two rows with the name value princess had before, now both of those rows have the value 5 in the lives column. In our database schemas, when we sort out what tables we need and what columns they should have, we generally designate for each table a primary key. The primary key of a table is the column or set of columns, the values of which are used to uniquely identify each row. In this example table here, it makes most sense to designate the make and color columns together as being the primary key, because presumably you wouldn't have two rows where the make and the color are the same. It would make sense, for example, to have two rows where the make in both is Toyota and the color in both is blue. because there's only one quantity of cars for each combination of make and color. In real-world practice, however, it's by far most common to give each table its own ID column, which has an arbitrary integer in it, a unique integer, and it's these ID columns which are most commonly used for primary keys. In this example here, you'll notice there's really no relationship between the ID value and the content of that row. It's really just totally arbitrary what the ID value is. The only important thing is that it stays constant for that row. To facilitate this use of integer IDs as primary keys, most databases have a feature whereby you could declare a column specially as a primary key column, and the database will actually auto-generate an ID number for that row. So when you insert a new row into the table, you don't have to specify an ID. In fact, you shouldn't. The database itself will actually automatically create an ID number for that row for you. This makes a lot of sense because it's then the responsibility of the database to ensure that that ID is actually unique, that it's not already being used by any other row in that table. What's called a foreign key is simply a reference to a primary key of another table. So here, for example, we have a table on the left of colors and a table on the right of people. And the color table has an ID column designated as that table's primary key. Again, the values in these ID columns, when we add a new color, they're generally just auto-generated by the database itself. For simplicity here, I simply have chosen values starting from 1 down to 5, just because it keeps the numbers simple. In a real database, when you insert rows, they might start numbered from 1, they might start numbered from 0, they might start numbered from any random number actually. So the IDs that get auto-generated aren't necessarily small numbers starting from 1. But in any case, looking over at the table of people, we have the name of each person, and then we have their favorite color. And the favorite color column is a foreign key because it's simply a recorded value that references the primary ID of another table, the color table. So according to the data in this table, the person named Alan, their favorite color is orange. And same for Chelsea, their favorite color is also orange. Sam, though, his favorite color is the one with ID 2, green. Now, the thing to note here is that primary keys and foreign keys are really what form the relationships between tables. In fact, the most common use of joins is to take two tables where one has a foreign key pointing to the primary key of the other, and once we take the cross join of those two tables, we then filter for the rows where the foreign key value of the one matches the primary key value of the other. And then we'd end up with this table, which is what we'd want when we wanted to query and find out, hey, that favorite color of Alan's, what's the actual name of that color? Because if we just query the person table itself, that only gives us the IDs of the colors. We want the actual name of the color, which is contained in the color table. Now, of course, the objection here is, well, why did we put the names of the colors in a separate table to begin with? Now, why not just stuff them into the person table, such that the person table has a column that simply reads color? That'd be far simpler. Well, in a trivial example like this, doing that would have probably made more sense. But as you'll see when we get into more complicated schemas, more complicated database designs, such thinking tends to lead you astray. In fact, as we'll discuss in a moment, there are formal rules that have been devised for how exactly you should split your data up into multiple tables in your relational database. Before getting into those more formal rules, though, there are first two simple guidelines which are very important to keep in mind. And those two guidelines concern how to best represent relationships which are called one-to-many relationships and what are called many-to-many relationships. First, a one-to-many relationship is like the one we just saw. For any one color, there are many people who might have that as their favorite color. So one color, many people. And the way this gets expressed is that we have the two separate tables, one for the colors, one for the people, and the people table has a foreign key pointing to the primary key of the colors. Or for another example, one person might make multiple orders. So if you have a table of people and you have a table of orders, the orders table has a foreign key referencing the primary key of the persons table. Now, the best approach for many-to-many relationships is less obvious because it involves the introduction of a third table. So here, for example, we have authors and we have books, and each author might have multiple books, but each book likewise might have multiple authors. The only way to properly express this is by introducing a third table which matches up authors with books. And this third table, you will note, actually has two foreign keys, one for author IDs and one for book IDs. And having more than one foreign key is actually perfectly fine. Foreign keys are not like primary keys. A table always has just one primary key, but it can have as many foreign keys as are necessary. Another kind of many-to-many relationship is when you have one kind of entity and you want to have multiple relationships between any pairs of those entities. Here, for example, we have a table of people and we want to express the friendship relationships between those people. We can't do that in the person table itself because each person has potentially multiple friends. So again, to express this many-to-many relationship, we have to introduce another table just for that purpose. Now, I should say it's actually kind of hard to identify the scenario as a many-to-many relationship scenario. It's a bit deceptive because you think, well, one person has multiple friends. That's one person, many friends, right? Well, the people that you are friends with themselves might likewise have multiple friends. So it's actually a many-to-many relationship, not a one-to-many relationship. It's pretty confusing in that regard. But in any case, looking at our other table of relationships, the other thing that makes this odd is that friendship we usually think of as a two-way relationship. It goes both ways. So when we say that person 1 has friend with ID 2, well, then we also say that person 2 is friends with person 1. If I'm friends with you, presumably you're friends with me. Presumably. Now, it's actually debatable whether you should have to express these relationships twice. You could establish a convention, a rule for your database whereby the friendship is only expressed in one direction. Maybe you'd have a rule deciding which way you would express that relationship, that two-way relationship. It's actually a bit of a dilemma. The downside of expressing the relationships both ways is that you have for one relationship 2 rows. And so if you want to update, modify, or remove some existing relationship, you'd have to make sure to do so in pairs. You'd have to make sure to remove 2 rows at a time, the 2 corresponding rows. On the other hand, if you chose to express these two-way relationships just by using one row, such that, say, you'd have person 1 with friend 2, but you'd omit the row person 2, friend 1, you could choose to do that. It would likely, though, complicate any query you wanted to do. Like you wanted to find out everyone who's friends with this certain person. You'd have to do a lot more work to figure that out if you only expressed the relationships in one direction. The takeaway from this is that the relational model is sometimes kind of an awkward fit for expressing certain things. In time, though, with some practice, you'll find that you'll adjust and you'll be able to fit most everything pretty easily into the relational model, and you'll find tricks to work around the odder cases. The formal rules I mentioned earlier that we use to devise the structure of our database, the schema for our database, these are called the rules of normalization. The primary point of the normalization process is to minimize any redundancies. That is, to ensure that when we insert new data into the database, we're only inserting it into one place, not multiple places. Not only do such redundancies lead to waste of storage space and to increased complexity in your queries, they also tend to lead to consistency problems, because if you record the same data in multiple locations, that means when you want to update that data or delete that data, you have to ensure to do it in all of those places all at once every time. If you're not careful, or if something goes wrong, you end up with data which has been half updated, so you have conflicting values in your database, which is generally not a good thing. The whole notion of normalization was actually originally devised by Edgar Codd himself, the person who invented relational databases, and in fact normalization was sort of an integral concept to the whole thing. Very shortly after he introduced the relational model itself, Codd also introduced the first 3 of what are called the normal forms. There's the first normal form, the second normal form, third normal form, fourth normal form, fifth normal form, and sixth normal form. Originally, Codd himself only introduced the first 3. The fourth and fifth were introduced by other people later in the 70s, and then the rule of the sixth normal form was actually devised and introduced actually quite recently, in about 2003, I believe. And the general gist of these normal forms is that they are progressive. So when you normalize your database, if you attain the level of the first normal form, you then from there can proceed to the second normal form, the third normal form, the fourth normal form, and so forth. So if your database conforms to, say, the third normal form, then implicitly it also conforms to the second normal form and the first normal form. Now, there's actually kind of a reason why the first 3 normal forms were introduced very early on, and then the fourth and fifth came later, and then the sixth way later. And that is that in practice, fourth normal form, fifth normal form, and sixth normal form are just not nearly as critical as normalizing your database up to the third normal form. Third normal form is actually what most people tend to aim for when they normalize their database. Most people don't fret too much about going beyond that. And actually it works out that in the large majority of cases, if you've normalized your database to the third normal form, it works out in most cases that the database most likely also conforms to fourth and fifth normal form without even trying. To be clear, it is possible to conform to third normal form but not fourth or fifth normal form. It's just not likely. It doesn't come up in most situations, really. So with that all in mind, we're only going to discuss the first three normal forms, because they, as I said, are really the ones really relevant to most people. Before we get to those, Codd himself actually summed up the purpose of normalization pretty succinctly. First off, the point is to free the collection of relations from undesirable insertion, update, and deletion dependencies. Again, relation is just Codd's term for what we usually call tables, and what he means by dependency here is a scenario where when you modify or insert or delete something from one table, you need to, for the sake of consistency, perform some other action on another table. Those are dependencies between tables. And while it's true that in some scenarios such relationships really are unavoidable, they're really necessary, one point of normalization is to try and minimize those dependencies because, well, the fewer the better. Codd also says that the point of normalization is to reduce the need for restructuring the collection of relations as new types of data are introduced and thus increase the lifespan of application programs. What he's saying here is that ideally when we add new tables to a database, it shouldn't require having to update existing tables or modify their structure. That would be quite bad and intrusive, right? It's really important to have the flexibility to add new tables as easily as possible. In bullet point 3 here, he says that the point of normalization is to make the relational model more informative to users. And what I think he means there by informative is that if someone were to look at the schema of your database, look at the design of the tables, it should be quite evident looking at any one table what its purpose is. What you tend to get in an improperly designed database schema is a bunch of tables that have sort of nebulous roles. You're not really clear on what purpose those tables serve or how they relate to the other tables. Lastly, Codd says that normalization is also for the purpose of making the collection of relations neutral to the query statistics, where these statistics are liable to change as time goes by. That's a bit tricky to parse, but what he means first by the relations being neutral to the query statistics, he means that the database shouldn't make it unduly hard to write certain queries because of how the database is structured. And not only should those queries be harder for a human author to write, they shouldn't be especially more onerous for the database itself to execute. But, of course, some queries you write are going to be naturally more complex than others, just because maybe they involve many more tables, and they're also potentially going to be more resource intensive. They're going to take longer for the database to process, simply because they involve more data and more work for the database to do. However, Codd is basically saying here that normalization will prevent scenarios where cases which should be simple and which should run fast aren't going to be artificially hard to write or artificially overly taxing on the database. That's basically what he's saying. So now let's actually look at the first of these normal forms. The first normal form is the easiest to state, certainly. It's usually just expressed as no repeating groups. Tables should not have repeating groups. The only difficult part about this first normal form is in understanding, well, what the hell is a repeating group? And there's a little bit of disagreement among competing interpretations of this first normal form, but at least what people agree on is that it means that there should be no ordering among the rows or columns in your table. And in practice, what that means is that when you insert data into your database row by row, you, the user of the database, understand that the database is not maintaining that order. And so when you do a query later on, you're not going to get back the data in the same order. That's, in practice, really what that means. No repeating groups means that you also shouldn't have duplicate rows. And in practice, really what that means is every table should have a primary key. As long as you have a primary key for every table, you're not going to have duplicate rows. No repeating groups is also interpreted as meaning that for any column, that column only really expresses one attribute. You shouldn't try and surreptitiously stuff multiple attributes into one. You don't want multiple values per column. And similarly, for every value in a cell, that is every intersection of every row and every column, each cell of data, it should never have more than one value in any cell. Which is kind of like saying the same thing that every column should just express one attribute. So the first normal form is really not hard to understand, even if there are maybe some competing interpretations for more subtle cases, but in general what I interpret it as meaning is just make sure your tables are really tables. No ordering of the rows, no ordering of the columns, one value per cell. And that's pretty much all it is. The second normal form is maybe a bit trickier. It's certainly more of a mouthful to say. No non-prime attribute is dependent on any proper subset of any candidate key. And to unpack that, we first have to define some of those terms. First off, what's called a superkey is just any combination of attributes of columns. It's any set of columns that could be used to uniquely identify each row. So in this example table here, there are a couple superkeys. The combination of skill and employee, that's a superkey. Skill and current work location would be a superkey, or the combination of all three together would be another superkey. What are called candidate keys, however, are a subset of the superkeys. The candidate keys are the superkeys which don't have any so-called extraneous information in them. It's a minimal superkey is one way to think of it. Another way to put it is that a candidate key would be a valid selection as the primary key for the table. And in this example here, there's really only one candidate key, and that is the combination of employee and skill. So once again, candidate key simply means a set of keys which could validly be selected as the primary key for that table. Now, what a proper subset is, if you forget, it's a subset which is not equal to the thing it is a subset of. So again, our candidate key here is employee and skill together. The two proper subsets of that are the employee column by itself and the skill column by itself. The combination of employee and skill together, that is a subset of itself, of employee and skill, but it's not a proper subset. So that's all what proper subset means. And finally, the prime attribute is a column which is part of a candidate key. So a non-prime attribute here is current work location because it doesn't belong to any candidate key. So to ask if this table is conformant to the second normal form, we ask, is the current work location column dependent upon either the skill column or the employee column? And the answer is that the current work location is dependent upon employee, because presumably it's something that corresponds to the employee. One employee has one current work location, right? So this is no good. We have a non-prime attribute which is dependent upon a proper subset of a candidate key. The most sensible way of correcting this example is to split it into two tables, one for employees and a second table just expressing the relationship between employees and their skills. This is actually an example of a many-to-many relationship. For each employee, there are potentially multiple skills which that employee has, and for each skill there are potentially multiple employees which have that skill. So if you just went by that guideline, you would very quickly see there's a problem with the original table, because one single table cannot express a many-to-many relationship. You have to bring in another table for that purpose. And actually, if we recognize that this is a many-to-many relationship, we should see here that there's still really a problem, and that is that the skills themselves should have their own separate table. And then this table expressing the relationships between the two would be between the primary keys for the employee and the primary keys for the skills. While the arrangement here might seem okay, it's going to become problematic as soon as we decide that skills themselves are something we want to provide more information about. As soon as we decide that a skill is something which is its own entity worthy of having its own attributes, that's when we'll want skills themselves to be in their own table. In a table in third normal form, every non-prime attribute is directly dependent upon every superkey. And remember, superkey means any set of columns which together uniquely identifies a row. And non-prime attributes are those attributes, those columns, which aren't part of any candidate key in the table. So the question is, what does dependent mean here? And actually there's a more popular, easier to remember formulation for the third normal form that makes this pretty clear. And the way this goes is every non-prime attribute provides a fact about the key, the whole key, and nothing but the key. And looking at an example here which violates this rule, we have this table of tournaments and their winners, which right off the bat, just saying that tournaments and winners should raise alarm bells, because tables should be about one sort of thing, not multiple things. But anyway, here the primary key of the table is the combination of tournament and year, assuming of course that one individual tournament is only held once a year. And so what we need to ask about the columns winner and winner date of birth here, the non-prime attributes, is are they providing a fact about the key, the whole key, and nothing but the key? And in the case of the winner column, that one does check out, but winner date of birth, again, right there in the name of the column, it's telling you that something's up here, because it's winner date of birth, not just date of birth. It's the date of birth of the winner, not of the tournament. So it's not a fact about the key and nothing but the key. It's really a fact about the winner. So the dependency here between winner date of birth and tournament and year, it's not a direct dependency here. It's a transitive dependency where winner date of birth is really dependent upon winner, and winner is what's dependent upon tournament and year. So the solution here, as basically always, is to take this table and to split it into more than one. And so more sensibly, we'd have a table for tournaments and a table for winners. And the winner table has a ID primary key, and the tournament table simply has a foreign key referencing the primary key of the winner table. So that's an example of third normal form, and again, understand that if you're in third normal form, then by definition you're also in second and first normal forms. And if you want to sum up all these rules into just one common sense slogan, that is to always ask yourself about any table, does this column really belong to this table? And if you just think in those terms, you'll usually catch most of your problems. Just going by that guideline will usually get you most of the way there to third normal form. Finally, one last thing to understand about normalization is that more normalized isn't always better. It turns out there are actually cases where one would actually want to deliberately denormalize their database. That is to take their schema, which is properly normalized, and to actually make it less normalized. Effectively to add more redundancy into your tables, into your schema. And the reason you might do this is for the sake of performance. Having redundant data, it sometimes can allow for more efficient queries, depending upon what exactly your use cases are. So in practice, we really have this trade-off. If you want to have a very clean database with everything properly organized, then you maximize your normalization. If you realize that, wait a minute, there are these few particular cases where we really need to have this data also in this column, because trying to join it together with all these other tables and get our data that way, that's just too inefficient for something that we're doing maybe many times a minute or something. And so in those cases, you actually deliberately denormalize your database and add in some redundant data. So denormalization is a tool basically of optimization. And database optimization is a whole subject unto itself that we're just not going to get into here. When we create a table, we have to specify the data types of each column. And in SQL, there actually is specified by the standard a certain set of data types that must be supported. Unfortunately, this is one of the areas where the databases, the various SQL databases, are most divergent, because generally there's a lot of overlap, because obviously every database needs a type for text, a type for numbers, a type for binary data and dates and so forth. But even within that small domain, there's a lot of variation. At the very least, even in just what to call the data types. So you'll have examples where these two databases have the same data type, they just give them different names, which is quite annoying. But if forced to produce a list of data types available in most of these databases, this is what I'd give you. First off, of course, we need number types. So we'd have a type for integers, here called integer, which is usually a fixed size integer, an integer of a certain number of bits, whether that's 32 bits or 64 bits, would depend on which database we're talking about. And then you'll usually have some number of float data types, here float and double precision. And actually these are the names prescribed by the SQL standard. And yes, when you write double precision, you have to write out double precision. You can't just write double like you would in C or Java. And those two, of course, are floating point types, where float is 32 bits and double precision is 64 bits. And then numeric is the name usually given to the decimal type. And for this type, we actually have to specify in parentheses first a precision and then a scale. Precision meaning the number of significant digits, and scale effectively meaning how large the magnitude of the numbers can get. How many zeros can you put at the end? For text data, SQL databases usually have two types, one called char, the other called varchar. For both of these, we specify in parentheses a number n, which is the maximum number of characters. The difference being that in a char, each value always takes up that full n number of characters, whereas in a varchar, the database may actually truncate by its own discretion. It may actually store the data with fewer than n number of characters if the data doesn't need the full n characters. So you can have a varchar and say like 4,000, but then you have just a short couple words in there for the value, and it'll be stored not as a full 4,000 characters, but just as however many are needed. And then for dates and times, we have date, time, and timestamp. Date being just the day of the year, time being just the time within the day, and timestamp being both together. And finally, we need some data type for storing just arbitrary binary data. And usually that data type is called blob, as in binary large object. So if there's some binary data, like say an executable file, which you want to store in a database, then that has to be stored in a column which has been declared to have the data type blob. Again, what data types are available exactly and what they're called, that differs significantly from one database to the next. This link at the bottom here takes you to a Wikipedia page with a good chart showing all of the data types available in all the popular database systems and what they're called. So now we can finally get into looking at some real SQL code. First off, we create tables with a statement beginning create table, and then we specify the name we want for this table, and then in parentheses we list columns, the names of the columns and their data types. And at the end of the statement, as with all SQL statements, we should put a semicolon. So this statement here, for example, we're creating a table called cats. We're giving it 4 columns, one an ID column of type integer, of course, and then a name column with varchar of 100, that is, its string values up to 100 characters long. Then there's a lives column of type integer, that is, how many lives does this cat have left, and weight, the weight expressed as a float, so like 12.0 or something like that. You may notice that I'm writing all of the SQL reserved words, the special words in the SQL language. I'm writing them in all caps, which is a common practice, but actually not required because the reserved words are not case sensitive. We can write them in any case we want. As for the identifiers, the names that we ourselves are creating, cat's ID, name, lives, weight, those things, by default in most databases they're not case sensitive either. Some databases though actually have a configurable option where you can turn on case sensitivity for table names and column names and so forth. Now in our example we created a primary key column called ID and of type integer, as we generally should for basically all tables, but recall what we really want for our primary keys is for the database to auto-generate these integer numbers for us, so we don't have to remember which IDs we've used and which we haven't. And the way we do this is we declare this column, this integer column, as a primary key with the reserved words primary and key. And now when we add new rows to the cats table, we don't have to provide an ID, it gets auto-generated for us, and the database will ensure that the ID generated is unique and not otherwise used already in that table. So that's how to create a table. To remove a table from the database, we use the drop statement, and you just write drop table and then the name of the table. So here drop table cats will remove the cats table from our database. And be clear that this will destroy the data in our cats table, so any data we've inserted will get lost. If you wish to modify an existing table by giving it a new column, we can do so with the alter statement. We write alter table, name of the table, and then add, and then the new column, with both the name for the column and the data type afterwards. Likewise, we can remove existing columns by writing alter table, table name, drop, and then the name of the column, just the name, not the data type. And finally, we can actually change the data type of an existing column by writing alter table, table name, alter column, and then the name of the column followed by the new data type. And understand that in most databases, when you modify a column like this, change its data type, you actually wipe all the existing data in that column. So it's effectively like you really just deleted the column and then added in the new column with the new data type. I believe in some databases, though, for some kinds of conversions, like say converting from an integer value to a floating point value, I believe in some cases that it may actually do a conversion if such a thing is possible, depending upon what you're converting to and from. But really, if you find yourself really needing to modify an existing table while preserving the data already in a column you want to change, well then you just extract all the data from that column into your application, have your application do the conversion that you want, assuming one actually makes sense, and then stuff the data back in. So there's always ways around this, of course, and changing your existing tables is not something you do on a regular basis. That's like a design change of your application. It's not something done in the normal course of business. To insert data into a database means to add a new row into a table. So the insert statement, we write insert into the name of the table, and then the reserved word values, followed by a pair of parentheses with a list of values separated by commas inside. So here we write insert into cats, followed by the reserved word values, and then in parentheses, a string mittens. Strings in SQL are always enclosed in single quotes, and then the number 9 and 12.0. And you may be wondering, well, which columns do these values get assigned to? And the answer is it's the same order as when we declared the table itself. So when we declared the table, we had the 4 columns actually. First we had the primary key, but that value is being auto-generated by the database itself because it was declared as a primary key. And then after that we had the name field, the name column, and then we had the lives column, and finally the weight column, which is a float value. So this relies upon us remembering the order in which we declared the columns. Though of course, remember, in a table there's no concept really of order between the columns, except for this purpose. There actually is an alternate syntax where you can specify the names of the columns, so you don't have to remember what order you originally declared them in, but we won't cover that. It's a trivial variation, but I'll leave it to you to look it up. To remove rows from a table, we use the delete statement and write delete from the name of the table, the reserved word where, and then the predicate. Some Boolean expression, basically. So here, for example, we're deleting from the cats table every row in which the lives value is less than 3. To modify data in existing rows, we use the update statement, and we write update the name of the table, the reserved word set, and then one or more column values, which come in the form of key value pairs, effectively the name of the column, equal sign, and then the value assigned to that column, and we separate these all by commas if we have more than one. And in this form, we're not specifying any predicate to select rows, so this will actually update every single row in the table. So here, when we update the cats table, and we assign 5 to the lives column and 9.0 to the weight column, those two values will become the lives and weight values in every single row of the table. If we wish to update only certain rows in the table, we append a where clause, which specifies a predicate. So here we have the same thing, but with a where clause with the predicate name equals the string fluffy. And this is confusing because in the set clause, the equal sign is used as an indicator of like assignment, whereas in predicates, the equal sign is used as a conditional operator. It's performing a test, returning true or false depending upon whether these two values are equal. This is the equivalent of what we would write in, say, Python or Java as two equal signs, rather than just a single equal sign, which in the vast majority of programming languages is used for assignment, not for a quality test. But in any case, in this update statement, then, we are updating the value of the lives and weight column, but only in that row or rows where the name of the cat is equal to Fluffy. To perform a query, we use the select statement, which in its simplest form is written select, then one or more column names listed separated by commas, the reserved word from, and then the name of the table. So here are two examples. First, we're selecting the columns name and lives from the table cats, so we get back a table as the result of our query, which has two columns, name and lives, and has all the rows of the cats table, but just with those two columns. In the second example here, though, we don't specify any column names, we just use the special symbol asterisk, which is used as just a shortcut for saying I want all of the columns from this table. So select asterisk from cats will return effectively the entire cats table with all of the columns. Now in the SQL statement here, where it's calling for us to specify a table, we can actually specify a table produced from a join. Because, well, a join does produce a table, right? So we should be able to query such tables. So here we're selecting asterisk all columns from the join of cats and dogs. So this first query will return the cross join of cats and dogs with all of the columns. In the second example, it's the same deal, except instead of a cross join, we're doing a left outer join. Remember, commonly we call left outer joins just left joins. We could actually write left outer join here, and that would also be acceptable, but SQL, most commonly, we just write left join. And then finally, in the last example, again, it's the same deal. We're doing a left outer join between cats and dogs. Recall, though, that outer joins and inner joins, unlike cross joins, may have a predicate which is applied to filter the rows returned by the join. So here this is a left outer join with the predicate specified in the on clause of cats.lives equals 6. And cats.lives here is the notation we use to specify the lives column in the cats table. And this may be important because the cats table and the dogs table, there are cases where those two tables we're joining together might have columns of the same name. So we have to use the syntax of writing the table name dot and then the name of the column to specify precisely which table we're referring to. So the join that's performed here, remember an outer join is first effectively an inner join. So we're inner joining cats and dogs together and then filtering on the predicate, filtering to keep only those rows where cats.lives equals 6, and then because this is an outer join, a left outer join, we are then going to add back in any rows from the cats table which by that filtering process are no longer present after the inner join. And so the outer join adds those back in, matching them up with null values in the dogs columns. I should note here, if you're wondering, the syntax of SQL is free form. That's why we have semicolons at the end of our statements. So the fact that we're indenting the on clause and putting it on its own separate line, that's just basically a matter of style. And to make what's going on in the syntax clear, we can actually put parentheses around our joins, so it's clear that it just produces one single table from which we are then selecting columns. So the parentheses in these three examples aren't really doing anything, they're just making it more explicit what's really going on. We're performing joins here and then using the product of those joins as the tables upon which we are performing select statements. Now, in any select statement, we can add an optional where clause, which is another predicate used to filter the rows. So here we're taking our last example and adding on a where clause that's filtering for the rows in which cats.name equals dogs.name, so those rows in which the cat and the dog have the same name. And you should be absolutely clear about when this predicate is applied, especially in relationship to the predicate of the join itself. The join with its predicate, that is performed first, and then we are selecting columns from that product, and then we are applying the where predicate. Then we're filtering the rows with this additional predicate. Now, if you wish to group your query on one or more columns, you add a group by clause, which is simply written group by and then the name of the column on which you wish to group. Again, here we're qualifying the name of the column with the name of the table, just in case that dogs also happens to have a column with the same name. And if you then wish to filter the rows after the grouping, you use the having clause. And what's special about the having clause, unlike the where clause, is that in the having clause you can use aggregate functions, which is not the case with the where clause in most SQL databases. So here we're grouping cats by age, and then we're using the aggregate function min to get the lowest weight out of each age group of cats, and we're filtering those rows in which the minimum weight for that age of cat is greater than 10. Now again, you should be very clear about when these various predicate clauses, the on clause, the having clause, and the where clause, you need to be clear about when exactly they get applied, when their filtering gets done. And the on clause is it's a predicate applied in a join, so it's performed during the join, you can say. The having clause is then applied immediately after grouping, assuming there is any grouping. And then the where clause is it's the final filter on all the rows returned by the select, so the where always comes last. Now, in our various SQL statements, in our update statements, our select statements, our delete statements, and so forth, there are cases where the syntax is calling for us to provide some table or some value or some set of values. And while normally when we provide, say, a value, we do so by just writing the value ourselves in our SQL code, it's possible to use a subquery, that is to use a select statement within another statement. And then if that select statement, say, returns a table, then we can use it in a place where a SQL statement is expecting a table. Or if a select statement returns a table with just a single column, then we can use that select statement in place of where SQL expects us to provide a list of values, a set of values. And finally, if a select statement returns a table with a single row and a single column, that's effectively a single value, right? So we can use such a select statement in place where SQL is expecting us to provide just a single value. Now, to provide an example of a subquery, I'll actually introduce first a new operator, the in operator, which takes a value and then after it a set, usually expressed as a list of values in parentheses. And the in operator is a conditional operator which evaluates to true if the value is found in the set, and otherwise it returns false. So our top example here, imagine that, say, this is a where predicate, and it tests whether the value from the column cats.lives is found in the set of 3, 6, and 5. So if cat.lives is equal to 3, or equal to 6, or equal to 5, this will return true, otherwise it will return false. In our second example here, we're expressing the value not as a column name, but as just a fixed value, the value 4, but we're expressing our set not as a fixed set of values, which we write ourselves in the code, but as a subquery. It's a select statement which is returning a table with a single column, the column age from the table dogs. And so this in operation here will evaluate to true if the value 4 is found in the column age of the table dogs. Aside from in, we have a number of other operators which deal with sets, and these are actually combinations of the existing comparison operators, the equality operator, the less than operator, greater than, less than or equal to, greater than equal to, etc. It's those operators, but then followed with either the reserved word any or all. And that turns these comparison operators into a comparison not between one value and another value, between a value and a set. And so in our top example, this is an equals any operation with the value from the column cat.lives, testing whether it is equal to any value in the set 3, 6, and 5. In truth, an equals any operation is really just the same as an in operation. Swapping out equals any for in here would do exactly the same thing. In the second example, we have a less than or equals all operation, which is asking, is this value less than or equal to all of the values in the set? So, is 5 less than or equal to all of the values in the set returned from the column age in the table dogs? So, assuming the ages in the dogs column are, say, 7, 8, and 7, this will return true because 5 is less than both 7 and 8. If the ages in the dogs column, though, includes any value which is less than 5, then this would return false. Now, subqueries can be pretty tricky to understand, and I know I'm going over them quickly, I'm kind of glossing over them, but I will make one last point which is very important, and that is you need to understand when subqueries are really performed. In this example here, we have a select statement which is selecting all the columns from dogs, but then we're filtering those rows with the predicate dogs.name in, and then a set provided by a subquery. And this subquery, you will notice, is selecting the name column from the cats table, but then it has its own predicate, its own where clause, which is filtering on a predicate using not just a column from cats, but a column from dogs. And this doesn't make any sense if you assume that the subquery inside the other query is performed first, which is kind of sensical because you would think, just like in sub-expressions, expressions contained within expressions, that you would evaluate inside out. But that's not always the case with subqueries. What's actually going on here is that the subquery in the where clause is being evaluated multiple times. In the containing select statement, the outer select statement, we are filtering each row of the dogs table, and this subquery in the predicate is actually being reevaluated for each row of the dogs table. And that explains how we can use a column from the dogs table in the predicate of the subquery, even though the subquery itself doesn't involve the dogs table, at least not in the from clause. So once you understand when the subquery is actually being performed, then you can understand how it works. The remaining question, though, is whether this is a good way of going about getting these results, because performing this subquery for every row in the dogs table sounds really quite inefficient. And the answer is that in this case, no, you probably wouldn't do things this way. It's much more obvious if you simply just join the dogs and cats tables together and then use an on predicate to filter for the same condition of cats.name equals dogs.name. This gives us the same results, though actually to make it exactly the same, we'd have to specify the columns we want with name, because actually we're selecting for all of the columns now in both the dogs and cats table joined together, which is not what we originally wanted. We just wanted originally the columns from the dogs tables. But otherwise this gets us the same thing. Now, whether one of these actually ends up being more efficient than the other really depends upon the database, because databases generally try and do very aggressive optimizations such that they might take your query and then produce a optimization plan, a query plan, that does something quite different to get the same result. So it could be the case in certain databases that these two queries actually trigger really the same internal actions and therefore take the same amount of time to perform. At the very start of the unit, I talked about how in a database, the interactions of clients with the database are done in these units of work called transactions. And while we haven't talked about transaction thus far, all of the SQL statements we've covered so far actually have to be performed in the context of a transaction. So how do you do that? How do you put things in a transaction? Well, first off, you just write start transaction, then you list your statements, whatever work you want to do, and then when you're done, you end with a commit statement then triggering all of the changes you made to be committed to the database, to be made persistent in the database and made visible to subsequent transactions. Now, I did mention there are certain scenarios that might arise in the course of a transaction which would require the transaction to effectively be aborted, for all of the changes you're making in the transaction thus far to be discarded. And when that happens, that's called a rollback. All the changes you make get rolled back. Usually this is triggered by something in the database which then notifies you, the client, of, hey, we aborted your transaction, we rolled it back. In some cases, though, you, the client, may have reason to wish to roll back the transaction, to abort the transaction. And for that purpose, you can then end your transaction not with the commit statement, but with the statement rollback. Now, earlier when we discussed transactions, we talked about ACID, atomicity, consistency, isolation, and durability. And when we talked about isolation, we mentioned that in practice, we don't always want perfect isolation because it tends to degrade performance with a high demand database, a database which is being taxed by the clients making requests of it. So in the SQL standard, there are actually specified 4 different levels of isolation, with at the top the most isolated being serializable, and at the bottom being what's called read uncommitted, which is basically no isolation. What characterizes the difference between these levels of isolation is the locks, if any, which these levels will acquire on the rows of a table in the course of a transaction. In the highest level of isolation, serializable, a transaction will acquire all 3 kinds of locks. It will acquire write locks, read locks, and range locks. Locks are a tool used to resolve concurrency issues, which work by simply acquiring a so-called lock on a piece of data, that is, staking a claim on a piece of data such that all other actors who wish to use that piece of data either are prevented from using it while it's locked, or those other actors are expected, if not required, to check and see whether a lock has been acquired on the piece of data before that actor attempts to use the data. So these locks are not necessarily like going into a room and locking the door so no one else can go in. It's more like hanging a occupied sign on the outside so no one else tries to come in. And the difference between a write lock and a read lock is that a write lock, once acquired, prevents others from writing the same data, whereas a read lock, once acquired, prevents others from reading it. And a range lock is a lock that neither prevents reading or writing. It's just a fixed selection of rows, basically. The idea of the range lock is that in the database, in the course of a transaction, say, if you perform a query where you filter for the rows where column X is less than 100, you want to make sure that the range of rows selected is the same in subsequent queries of the same transaction. You don't want the selection of rows to be affected by something that happened in some other transaction that overlap with your own transaction. So that's what range locks are about. To understand the effect of these different isolation levels and the effect of these locks, it's actually easiest to think in terms of what kind of undesirable situation do these different isolation levels avoid. And there are 3 effects that arise if we lack isolation, and these are what are called dirty reads, non-repeatable reads, and phantom reads. And notice how they correspond to the locks. When we use all 3 locks, including range locks, we avoid phantom reads. When we use just write locks and read locks, we avoid also non-repeatable reads, and when we use just write locks, we avoid at least dirty reads. So what exactly are these phenomena? Well, a dirty read occurs when in a transaction, let's call it transaction X, we read some data which has been updated by some other transaction, let's call it transaction Y, but that data was not committed by transaction Y. So transaction X is in effect reading some data which has not really been committed. It's been modified in the database, but not properly committed. This is generally undesirable because that uncommitted data, there's the possibility it might get rolled back for whatever reason. And there's also the possibility that within transaction Y, when that data was updated, there's some other piece of data that's meant to be updated with it somewhere else in the database. And so you sort of have this consistency problem where you have this half-updated data, and transaction X might end up getting one part of that data update without getting the other parts. Like, say we have the database for a flight booking system, and in the course of an update, when some customer buys a seat, we're updating that, hey, here's this new customer, and oh, here also is the seat in the plane, which is no longer available. If at the same time we have another transaction triggered by a customer trying to find out whether a seat is available, they might erroneously see that the seat is still available, even though in the database in another table it's been remarked that, hey, this customer has purchased this seat. So this could lead to a situation where two people end up buying the same seat. The phenomenon of a non-repeatable read is a situation in which during a transaction we read the same rows more than once but get back different values even though we in our transaction haven't modified those rows. This can happen in the course of your transaction if in another overlapping transaction the data is being modified. The first time you read the data was before the other transaction modified the data, and the second time you read the data was after it was modified by the other transaction. Arguably, this scenario is not a huge concern because why are you reading the same data twice? That sounds kind of inefficient. Why didn't you just read it the first time and stick with that? Well, sometimes it does come up though, and sometimes it'll matter whether or not the values are the same or not. And as is always the case in concurrency, whether these bad reads, these dirty reads, non-repeatable reads, and phantom reads, whether they're really a problem depends upon really what you're doing in your application. But there are situations where you do have legitimate cause in the course of a single transaction to query the same data twice, and there are situations where you don't want that data to read any different the multiple times you read it. Lastly, the phantom read scenario occurs when, in the course of a transaction, you perform the same query multiple times and get back different rows. So the non-repeatable read situation is when you get back different data in the same row. Phantom read is when you get back different rows entirely. And this may occur because the conditions upon which you are filtering, the predicates, they may say something like column x less than 100. Well, if data changes, the rows in which x is less than 100 may change, so you get back different rows. And this is why at the highest isolation level, serializable, most databases employ what are called range locks, a lock on a selection of rows, such that if you perform the same query with the same semantics, you will get back the same set of rows. Now, to make it absolutely clear why a range lock is necessary, when you perform a query and you get back a certain set of rows, and even if you have a write lock and a read lock on all of those individual rows, some other transaction might modify data in other rows such that those rows then fit the criteria of your filtering predicate, so they would then get included in your query, and your query that you perform the next time will actually return different rows. Range locks prevent that by, in the query, fixing the set of rows that get returned by that query such that the next time you perform the same query, you get back the same rows. The last thing I'll note about these concurrency issues and isolation levels is that some databases don't actually use locks. They use a different technique. They use what's called multi-version concurrency control. Postgres, for example, uses multi-version concurrency, and that's actually why, until recently, it actually only supported two different levels of isolation. It supported the highest level, serializable, and it supported the lowest level, uncommitted read. So it was an all-or-nothing approach of total isolation or no isolation at all. The gist of multi-version concurrency is, as the name implies, to provide a different version of the state of the database to each transaction, what's called a snapshot. So when I initiate a transaction, I get a fixed snapshot, a fixed view of that current state of the database for my very own, and when I work with the database, I just see things in that state. When I make changes in the course of my transaction, those changes are generally given a timestamp, and then when I try and commit, there's a reconciliation process of my transaction reconciled with the other transactions that may have overlapped. At the time I commit my transaction, there may end up being a conflict, which may call for rolling back my entire transaction, but generally, more often than not, it'll go through. Last thing we'll do in this unit is go over some of the aspects of relational databases that we won't cover in any detail. First off, the so-called security model of a database refers to how it handles security. And for most SQL databases, the gist is that the client, when it contacts the database server, has to log in and has to provide a username and a password. And associated with each user account in the database is a role, which describes what kind of privileges that user has, whether they can modify this table or read that table and so forth. And of course, this is all set up and controlled by users with special administrator privileges. Beyond that broad outline, the details of how security works in one database compared to the other tends to vary significantly. It's something you pick up when you work with one particular database. What's called a view in a SQL database is a special kind of table. The normal tables in the database are called base tables. A view you can think of as a virtual table. It's a table which in a sense doesn't really exist because it doesn't have its own data. It's simply a view into other tables, into the regular base tables and possibly other view tables. And the way this works is you define a view and you simply define it by a query, a select statement. And so a view in effect is pretty much just an alias for some particular query. It's really not much more than that, though in most cases the database will allow you to modify the data of a view table, and what happens then when you update a row of a view table is that the actual row from the base table from which that data was derived, that gets updated. So a view is not exactly just an alias for a certain query, but it's pretty close. Stored procedures in SQL are in effect basically functions within the SQL language. A stored procedure is just a list of statements to execute when that stored procedure is invoked by name. Now, stored procedures are one feature of SQL that's highly divergent. Some of the databases provide more features than others. In some, you can go as far as basically using SQL like a Turing-complete language. It's like almost a full-fledged general-purpose programming language. It's just a really, really awkward one. What's the point of having stored procedures? Well, one major advantage potentially is that if you so choose, you can put all of the complex queries of your application into the database itself as stored procedures. That way, when your clients access the database, they don't have to send a whole bunch of SQL. They can just send very simple commands saying simply, call procedure X. And first off, that could spare your client and server from exchanging quite a bit of network traffic, at least in the request. In the response, of course, the client still has to get back all the data. Another potential advantage is that by having the query predefined as a procedure in the database can parse the SQL ahead of time and also optimize the query plan for those statements. It doesn't have to do that on the fly with each new request. And of course, the more complex the requests, the more overhead that saves. Another potential advantage of stored procedures is that they can, in effect, serve to simplify the interface to the database. Rather than having the clients devise their own complex queries, they're just interacting through a set of predefined queries by name. And you can actually configure security policy to enforce this. You can restrict clients to only using certain stored procedures and disallow them from making just arbitrary queries on your database. So stored procedures can also be a useful tool in security. Finally, one more potential advantage of using stored procedures is that stored procedures can do logic that's more complex than you can otherwise do with just regular queries. This is particularly the case when we use stored procedures in conjunction with another feature called cursors. Cursors are effectively iterators over result sets of queries. Using a cursor, a stored procedure can take the result set of some query and work through its data row by row or work with it in chunks of rows. So this allows the database to do more sophisticated kinds of processing on data than it otherwise could do. Indexes in SQL are an important tool of optimization. We attach an index to some column, and what the database then does is it creates an index of the values in that column, allowing for faster lookup. So for example, if in your queries you're going to be searching for particular ID values within some table, the primary key ID values, it'd be a good idea to put an index on that primary key, and that will allow the database to find particular rows with a particular ID much faster, because otherwise, without those indexes, the database would have to scan through the entire table to find the rows you want. And scanning through a whole table can take quite a lot of time, especially as more and more rows are added. Indexes can also be used to provide for faster sorting of a table. Say we have a table of people that includes their names, and we want to generally access this table in alphabetical order. It would be a good idea then to create an ordered index for the name column in that table, and the database can then use that index to do a quick sorting on that column when it needs to. Indexes are another part of SQL databases that are highly divergent, so you'll find that the way they work exactly in Postgres differs significantly from how they work in, say, Microsoft SQL Server. A trigger in SQL refers to some code, generally a stored procedure, which is automatically executed in the database upon the occurrence of some event, like say some particular row being updated. There are all sorts of potential uses for triggers. The most common, though, I would say, is to preserve the integrity of the data in the database. Like, say, when a value in this column gets updated or a row in this table gets deleted, that means we have to also change this other thing. Of course, that's the sort of thing you could enforce in your application code, the client talking to the database. Sometimes, though, that's not adequate, and you want the database to enforce these kinds of integrity rules itself. So that's where triggers come in. Be clear that SQL is not really a protocol. When a client connects to a database, it doesn't just open up a TCP socket and start spouting SQL at the server. That won't work because there's more to the protocol. Like, say, when a connection is made, we have to authenticate ourselves. We have to log in with the username and password, and that's not a part of SQL. So you may ask, what is the standard protocol used by databases? And the answer is, well, there really isn't one. Instead of having a standard protocol, the solution devised was a standard API, so to speak, what's called the Open Database Connectivity Standard, ODBC. So in an application, we use the ODBC library available for that language and platform, and the ODBC library is then responsible for translating that into the appropriate protocol for the database. Now, again, different databases have different protocols, so what you also need is what's called an ODBC driver. These drivers are basically plugins to the ODBC library, and each one enables ODBC to talk to a different database. So, for example, if I'm working in Python and I want to talk to Postgres, we would need first an OBC module for Python, and then we'd need an ODBC driver for Postgres. And understand that the ODBC standard is specified in C. So an ODBC library and the drivers it uses are always written in C. So because they're in C and therefore compiled to native code, you need to make sure that the library and driver are compiled for your platform. And if you're using some language other than C, you need some way of invoking the C code from your own non-C code. In Python, this is not a big problem because Python makes it easy to call C code from Python. In other languages, though, it's a bigger issue, like say in Java. In fact, for the sake of Java, an alternative standard was developed called JDBC, J obviously as in Java. Java database connectivity is really the same idea as Open Database Connectivity, just written to run on the Java runtime rather than written in C. You'll find that there are freely available JDBC drivers for all of the most popular databases, but for some of the more obscure databases there may not be any JDBC driver available, so the solution there is to use what's called a JDBC to ODBC bridge, which, as the name implies, takes the method calls you make using the JDBC API and translates those invocations into calls to an underlying ODBC library. So that's a solution for the scenario where you're using Java, but the database you want to connect to only has an ODBC driver, not any JDBC driver.